see if we can apply, I hope that addresses your question. So now let's see if we can apply some of the same ideas, the same logic, and figure out what's going on with known as a deactivating group. So first, we asserted earlier that if you have a nitro benzene, shown here, and we wanted to add a second nitro group, the reaction occurs 100,000 times slower or something like that. And we said this is an electron withdrawing group. So we could actually either, I first said induction, withdraw electron density from the ring, or even write a resonance structure here as well, which is shown on the bottom. So this actually, the nitro group is withdrawing electron density through induction and resonance. So this is bad news if you want to use the benzene ring as a nucleophile. You want it to be electron rich. Instead, what the nitro group is pulling a lot of electron density away from the ring. So it still can act as a nucleophile, still does have electrons that act as a nucleophile, but it's far less reactive than benzene alone. So this is an example of a deactivating group. And it's actually a strong deactivating group. And we'll define strong and weak here soon. The other observation is that, as we mentioned here, is that the nitro group ends up predominantly in the structure in the middle, the second one. So it's the meta position. So this deactivating group, the nitro here, appears to be a meta director. In other words, it's directing this second nitro group to be at the meta position. So let's see if we can use the same resonance structure argument now to come up with why meta would actually be the major product. And that's on this next slide here. So this is showing the same idea as before. Let's put the nitro group, and there's two nitros, but now that's the second nitro group at the ortho position. And we can draw a carbocation intermediate and draw a couple of resonance structures for this. We can do the same if we put the nitro group at the meta position, resonance structures as well, like in the middle, and the same thing on the bottom for the para attack. Now, what ends up happening, though, is in the top in the green box here, the carbocation, even though that's on a carbon that would be tertiary with 3 different groups attached to it, this carbocation in the green box has this positive charge right next to this nitrogen, which actually has a positive formal charge. It would be N plus and O minus. So this is energetically highly unfavorable. We have these two positive charges right next to each other. So this would be the least stable resonance structure within the hybrid due to those positive charges. Same thing on the bottom for the para attack. This carbocation now is situated right next to the positively charged nitrogen. So energetically, highly unfavorable or bad news, right, in terms of the carbocation stability. So now the green box actually represents something that's unfavorable. Unfavorable. This one's also unfavorable. Should have a red box or something around it, maybe rather than green, from the image that I stole from, actually, this time I actually cited the textbook. This is from the Klein textbook. Now, when we look in the middle case here, the meta attack, the carbocation actually is never on that carbon that is directly attached to the nitro group. So in a way, energetically, this is making the best of a bad situation in the middle with the meta attack. You avoid that highly unfavorable resonance structure. So this is the least bad, if you want to think about it that way, which then should end up being energetically preferred. And to keep with our love of free energy profiles, we can show that here in that the amount of energy it takes then to form now this resonance hybrid having the carbocation right next to the nitro group is some high amount of energy. However, it's less bad having a resonance hybrid that avoids that structure. So the structure, the energy profile, I should say, to form the meta attack, is going to be lower in energy, or preferred. And the pair is also energetically unfavorable now here. And now the ortho and the pair are somewhat similar, even though the ortho should be a little bit higher because the nitro groups are bumping into each other. But they chose to not illustrate that here. But the major point is that by having the nitro group at the meta position, we avoided this unfavorable interaction. And as such, this would be the major product. So again, it's a lot of stuff. We have these ortho-para directors and these meta-directors. But what we can do is, I'll slide back for a second, is use these resonance structure arguments to help come up with a rationale as to why we see these different outcomes. So I wanted to squeeze in at least one more example, but I'll pause for a second again just to let us catch your breath and see it. Hopefully this is making sense so far. So Abbas asked, how could activating and deactivating groups be asked? So what we'll do in the end is, let me slide up for a minute to this end. I have it looks like a timeline, which we probably won't get to today, to think about what these different groups are and how they would affect the rate of the reaction. What we're going to see is, since I've shown this here, we'll end up seeing that most of the time, groups that are activating make the benzene ring more active are also ortho-para directors. And most of the time, the groups that deactivate the ring are meta-directors. A very important exception, which if we don't get to today, everyone will be really just in suspense until tomorrow, are these halogens are weakly deactivating but ortho-para directors. More specific to your question, Abbas, is that notice the groups that are activating, ignore the halogens for a second, oftentimes have a lone pair of electrons on the atom that's attached to the ring. And this is the next point. So they can actually dump electron density into the ring. The groups that are deactivating have electron withdrawing groups, but in the group that's the carbon in a lot of these cases, it's attached to the ring. So it's only pulling electron density away from the ring. And so one could be asked to predict if a group is activating or deactivating. And it all comes back down to induction and resonance. So let's use an example of that. All right, great, and thanks, James. Happy to hear it makes sense. Let's go to this one. And let's think about phenol. So we have a hydroxyl group here. And I don't know why I use nitration. I think it's just easier to write here. So now let's imagine we're going to nitrate phenol. Ah, Lorianne, ranking question. Thanks. Yeah, that sounds like a great idea. And yeah, actually I was planning on doing that. No, it's a fantastic opportunity for that. No, it's fine. No, it'll be all right. So now let's imagine we have phenol. Here we can add a nitro group, ortho, meta, or para. Now the order is slightly different than before. And just to help simplify it a little bit, you'd end up seeing that you have about 48% of the ortho. We're just going to say the same amount of the para. I'm simplifying. And if I did the math right, we'd have about 4% of the meta. So what that means is that ortho is a major product. Para, same format here. Para is a major product. And meta, can't seem to stay with that same format. Meta is a minor. Minor, meta. Okay? Now, on top of that, let's say that this reaction with the phenol and the nitration actually happens faster. It's like, we'll make up a number like 100 times faster. So what that means is that this group, the hydroxyl group, is activating. And importantly here, it's an ortho-para director. Because we're saying ortho and para as our two major ones. And for the ranking, normally, you don't normally have to rank between, for Kyle's questions, between the majors, the ortho and the para. However, between ortho, we'll group them together as groups that are ortho-para directors or meta directors. That will be important. However, deciding between them is the major product, the para or the ortho, not so much what we've been thinking about that. Okay, great. But we do need to come up with an explanation for why the ortho and the para are actually the major products. So let's consider resonance structures. When in doubt here, let's think about resonance. And we might not have time to draw all of them, but let's just put the nitro group first at the ortho position. So we start off with our phenol, and we're going to add NO2 plus at the ortho position. So let's put it here. We'll have a positive formal charge here. And now what we want to do is draw the resonance structures here. And I encourage you, if you would please, to draw them. Maybe you'll be ahead of me. Let's move these electrons here. Draw another resonance structure. Move these electrons down here. And so we have something like this. And there's actually one more resonance structure that we can draw, where we can use a lone pair of electrons on this oxygen. Well, I think I want to make that a red arrow. Yes, that'll work. All right, so now we have all of these different resonance structures. And when we're looking at the relative stability of all of these resonance structures, what we would see is actually this one here is the major contributor. And the reason for that is all atoms have an octet of electrons. So remember back in the good old days, again, of organic one, is that when looking at different resonance structures, you look at primary, secondary, and tertiary. However, if there's also a scenario where all of the atoms can have a full octet of electrons, that will oftentimes be the major contributor. And atoms like oxygen and nitrogen, sulfur, and so on can bear a positive formal charge and still have an octet of electrons. So this actually provides an explanation as to why maybe, okay, if attack at the ortho position occurs, this will at least be our major contributor to resonance stabilization. I will just assert now that if we draw attack at the para position, the same thing will happen. So what we need to do is, to complete this story, is let's think about what happens. That's not a good sentence. Let's think about what happens if the nitro group is at the meta position. So now instead, let's put our strong electrophile at the meta position. Again, we'll form an rhenium ion. The nitro group is here, procation, and we can take the same process, draw resonance structures. That's a valid resonance structure. So I need to put the positive charge there. Draw another one. Something like this. And then actually we're done. Those are all the resonance structures that we can draw. So the positive formal charge ends up never being on the same carbon that's attached to the hydroxyl group. So that in this particular case, the ortho and the para, which we haven't drawn here, ends up being the major product because the carbocation intermediate, if the substituent, the nitro group in this case, if it's at the ortho or the para position, can take advantage of this major contributor in the resonance hybrid, where every atom has a full octet of electrons. However, if the nitro group is added at the meta position, you cannot form that major contributor in the resonance hybrid. So it's less energetically favorable. Now, the one last point, if I can make, even though we've gone over here a minute, is that one of the things that sometimes is confusing, and it's certainly understandable here, is that the hydroxyl group here, it's electronegative. So it seems like it should be withdrawing electron density from the ring. They're like pulling electron density out of the ring. And indeed, that is true. But the thing to remember is this also is an OChem 1 fundamental concept is to, let's use the right conjugation here, the word, is to think about induction and resonance. And hopefully in the first semester class, you'd sometimes see this tug of war, like this energetic balance between inductive effects and resonance effects. And generally, resonance is more important, or it has a larger energetic effect. So what that means is that even though the hydroxyl group, the oxygen, can pull electron density out of the ring by induction, it can dump electron density into the ring by resonance. And that's what we're showing here in the resonance structure of the carbocation intermediate. And you could actually even draw resonance structures here of our starting material, where we move the electrons into the ring. We'd have multiple formal charges, but it illustrates that this hydroxyl group is dumping electron density into the ring. So then, if I may, in just the last 30 seconds here, I'll come back to that one if you didn't have a chance to write it all down. To summarize, what we're going to see is when we're thinking about these groups, these activating groups, which are generally ortho-para-directors, can dump electron density into the ring by resonance, strongly or moderately. And I don't want us to have to parse these out. Or notice these are more inductive effects. What we'll see next time is that the halogens, actually the inductive effect sometimes is kind of even more important in a way. So there's always an exception. However, these deactivators do not have a lone pair of electrons on the atom that's attached to the ring. So they cannot provide this resonance stabilization. So that allows us to think about activating and deactivating in terms of nucleophilicity, and importantly, in stabilizing the carbocation for the ortho and para attack versus the meta. So it's a lot of information, but hopefully we can start to see these trends again coming out. So we have these 5 major reactions. Now, when we already have a group on the ring, let's go back to a slide that shows that. We now need to think about, when I add my second group, is it going to be ortho-para as the major product or meta? And we can rationalize which product is the major product using inductive and resonance arguments, and knowing that resonance is oftentimes more important. So then, if I may, I know I said 1 minute or 30 seconds like 2 minutes ago, but just to help put this into context, because again, I know there's a huge amount of information, but what we're going to see now, we have our 5 reactions. We've described activating and deactivating groups, ortho-para directors versus meta directors. And so we'll talk about the halogens next time as to why they're a little bit different. We'll go through a couple more meta directors. And then we'll ask the question, what happens if you have 2 groups on the ring and you want to add a third? And it's applying the same logic as to what we've already seen. We have just a couple of other quick reactions to talk about, and then only 2 reactions with this substitution. So I'll post some more practice problems for these directing effects and the 5 reactions that we have. We'll piece those together next time, and hopefully see more of a summary as opposed to new information for these directing effects. We've gone through the bulk of that, so that now we have time to practice it. So no quiz until Wednesday.